Okay, so this afternoon I will complete what I was trying to tell you this morning about the structure of disks resolved by interferometry, and then we will discuss a little bit dust evolution and grain growth in disks. Before going there, I want to go to the feedback that I got from you. There were two main points in the feedback that you gave me this morning. One, very common, is that you basically could not understand what the Williams 2013 plot was all about. So I'll try to explain it again in the next two slides. And the other thing was having more references, well, some references on interferometry, on the techniques. So I added on the Facebook page these three references. These are on my own personal taste. It's full of books and articles on interferometry. The first one is a book on radio astronomy in general, but has a good explanation of radio interferometry and millimeter interferometry. And the last two are both freely available on the web, and you can go and have a look. The first one is more on classical interferometry, radio centimeter wave interferometry. The second one is millimeter, but is a little bit old. Okay. The Williams et al. Plot. So what we want to do here. That plot is complicated because I have to admit that I am from an old school. I always think that when you have to resort to complicated statistics, it means that you are desperate, which is the case here. So the problem here is that you are trying to compare samples that are very difficult to compare. Okay? And you want to extract a signal by comparing samples that have very different selection criteria and different sensitivity, okay? And so you need to be smart. That's why the process is complicated, because you have to do some work if you want to do this. So basically, on the left side is the plot of the masses versus mass of the central star in Taurus. This is the most extensive survey available so far. There are a lot of plots, a lot of points, and a lot of upper limits. And on the right side, you have one of those regions that I showed the comparison in the plot. And you want to figure out whether the typical masses that you derive here, that you observe here, are different from the typical masses that you have there. You cannot just do a two samples comparison, because the upper Scorpius survey is something like this, if you put in the same size. Is sampling a very narrow range in mass, so not the entire mass range, and has different upper limits than the one in the Taurus cloud. So basically, what you have to do, you have to extract from the Taurus sample, you have to extract some subsamples that most likely are like the one that you have in upper SCO. So what they did essentially was to extract randomly 10 to the 5, I believe, which is a fairly large number, a number of samples that are drawn from the properties of that sample there, and have the selection criteria of this sample appear. And then you can do the comparison one by one to see, using the statistical methods, for censored data, so data with upper limits, not a simple KS test, but something a bit more complicated, to check whether the two things are compatible. So your null hypothesis, if you want, is what is the probability that this random sample and this sample are drawn from the same distribution? That's the probability, okay? And you have n of these probabilities, because you have n samples. And then what you do here, you plot a cumulative function of these probabilities, essentially, okay? So this is the cumulative function of all the probabilities that you have computed. And basically, if the majority of your random samples are compatible with your observed sample in that star-forming region, it means that that star-forming region is similar to Taurus. If the majority of the random samples are totally different from the one that you have observed in your star-forming region, then your probability gets in the low part. And in this plot, only the sigma Orionis curve has more than 50% of your random samples, 50% of your random samples is here, that have probabilities smaller than the 3 sigma to be compatible. So this is a null hypothesis. So you are trying to negate the fact that the two are compatible, okay? That's the way it's done. Okay, and this is necessarily because you cannot directly compare the various samples. The uncertainties that you have, especially in the upper score and in the sigma Orionis sample, is that they contain very few detections and they mostly upper limits. And so essentially your probabilities, especially sigma Orionis, and so your probabilities are driven by where your upper limits are, which is as always a tough situation to be in, okay? I hope I have clarified this plot. Let's go back to the continuum emission from classical disks. And we were here. We were on how do we compare interferometric observations with models to extract the parameters of your disk, of the emission, continuum emission from the disk, the structure of the disk. So basically, what you do, you create a model of the disk that depends essentially on the surface brightness, on the surface density of material, so where you put the mass from the center to the outside, and on the stellar properties, and you solve self-consistently the radiation transfer, essentially. So you compute the temperature and so on in the disk and the emission of the disk. The parameterization that normally people use is the one that Phil also showed at the beginning of the week, which is the one that comes from the viscous evolution of disks. And basically, in this case, you try to solve for these 3 parameters, the normalization factor, essentially, how much mass there is at a certain point in the disk, the transition radius, and this gamma exponent. This formula essentially contains a power law part, which is essentially up to RT, okay, from 0 to RT, and then an exponential cutoff beyond RT, okay? So basically, you are trying to figure out where the exponential cutoff is taking over and what's the best power law that is fitting the part that is a power law, okay? And then you have a normalization factor, obviously. All right, these are what you get out of the data. So these are the data for 3 representative disks in Taurus taken from observations pre-ALMA, okay? So with the, in this particular case, with the Karman ray at 1 millimeter, you have the real part of the visibility as a function of the baselines on the UV plane. So essentially, close to the center of the UV plane, you are tracing the large structures, all the structure, and at long distances on the UV plane, you are tracing the small-scale structures in the disk, okay? And this is the results of the fit, essentially. This one is the surface density distribution that you derive as a function of radius in the disk. This is in astronomical units, so that's the sigma, okay? Then in this second plot, there is the cumulative flux as you go from the inside to the outside. And you see that at millimeter wavelength, basically, if you look at where most of the flux is emitted in the outer disk. So beyond, say, 10 to 20 AU, there is most of the flux is emitted. In this plot, you have the cumulative mass, which is essentially coming from this one, okay? And again, it tells you what I was telling you this morning, that basically most of the mass and the flux is coming from the outer disk. So if you say, I define more or less, that's my own personal definition, define inner disk within 10 a few AU and the outer disk what's beyond 10 AU. So most of the mass is in the outer disk, and these are the temperatures that come out of this fit, okay? As you see, the fit are relatively good, and there is a variety of surface density profiles that are derived in different disks. Some seem to go down in the inner disk. Some are flat and then fall off, and some are very high in the inner disk and go down. Okay, but again, remember that this line here is your angular resolution. Okay, I didn't say this. This is your angular resolution, so the angular resolution of your observation. So essentially, you are not resolving this part of the disk. You are fitting this part of the disk, and you are extrapolating using your, essentially, your formula into the inner disk. Okay, that's an important point. If you look at how this ensemble of disks look like, if you fit them this way, you have the results of two sets of disks modeled by two different groups in the past few years, and basically you have these are the parameters of the surface density distribution. I don't have the normalization for this, but the gamma values that you obtain are in the range from minus 0.5, roughly speaking, to 1. 0 means essentially a constant surface density in the inner region before the exponential cutoff, and negative values of gamma means that the surface density tends to go down as it goes close to the star. And these are the transitional radii, which, as for the same sample, plotted against the age. I wouldn't trust this too much. So the point that I wanted to make is that the transitional radii are between, say, 40 and 100 astronomical units. So the surface density in these disks of this dust in the outer disk fall off very, very fast after 100 AU. That's what you should get out of this. And you can see it also here, where some of these surface densities are plotted. The disks are not the same as this one, but a different set of disks. And you basically see that you have the internal power law, and then the exponential cutoff beyond, between 30 again here to 200 AU. Note again that basically we have real constraints, so we are fitting only this part of the disk, and this part is an extrapolation because we don't have the angular resolution to resolve it, okay? But given all these uncertainties, and using in this particular case a gas-to-dust ratio of 100, you see that many of these disks actually are expected to contain, to have material distributed in the same way and with the same amount of material that you expect for the solar system, roughly speaking, okay? These are very rough. Rough things. Note, however, that these are the brightest disks, obviously, because those are the ones where you start, because you need to have enough signal to resolve it, and so it's not obvious what the bulk of the disk population will look like in these diagrams. It's possible that the bulk of the population will have a lower values of sigma, and this is something that still needs to be investigated and requires the higher sensitivity that only ALMA can provide, and this data will become available soon because there are several ALMA programs that are actually looking at this now. Okay, one last point is that for these massive disks, these disks are relatively massive, you can look at the stability, again using the gas-to-dust factor of 100, and you can check whether there are regions in the disk where you know the temperature, you know the surface density, so you can check whether the self-gravity is important and whether gravitational instabilities may be present in some of these disks. And you see this plotted here, the value of Q, the Tomry Q parameter, and this is essentially the region where the disk would be unstable. You basically see that most of these disks are expected to be stable against gravitational instabilities. These are late stage, so they are not very young disks, except for a very few cases that approach the critical value, or maybe even go below the critical value. And you can see that the region in which this occurs is between, say, 30 AU and 100 AU, roughly speaking, okay? So this intermediate region before, obviously, the exponential cutoff. When you have the exponential cutoff in the surface brightness, in the surface density, then you don't have enough mass to go there. Okay, so what ALMA can bring to you, obviously can bring you angular resolution and sensitivity. So you all have seen this image, I suppose. This was the best image of this disk that was available before the ALMA observations. And more or less had the same angular resolution of the previous observation that I've shown, okay? So it's comparable with the previous thing. And essentially they found similar results for this particular disk. So a surface brightness, a surface density distribution that is sort of flat in the inner region and then has an exponential cutoff. And again, using a gas to dust ratio of 100 that could compute the Q parameter. And they see that essentially again in the region, since this is one of the most massive disks known, is actually a very young source. In the region between, say, 50 and 100 AU, maybe the disk could be unstable, okay? This is the ALMA observation, and unfortunately it's not very clear, but I assume you have seen the image. It's a series of concentric rings as it appears. If you do a cut of the intensity profile, you see that essentially this is the intensity profile, okay? And you see these rings that give you a contrast in the intensity, which is of the order of a factor of 2. The angular resolution of this image now is of the order of 4 to 5 astronomical units. So it starts to resolve the scale height actually in the outer disk. It's smaller than the scale height in the outer disk. And interestingly, this, well, obviously one of the questions that I have for your discussion later on when there will be the 5-minute pause is what is causing these rings. So don't start thinking now, you will have that at that time. But interestingly, this dark patch here, no, this dark ring here, exactly falls is this range here that I plotted here. Exactly falls in the range where the disk was predicted to be gravitationally unstable. So obviously, an obvious thing to do is to look and see whether you find something. And before doing that, I wanted to show you why it's so difficult to do these observations and why we had to wait for ALMA. So we are basically here, no? And our hotel is there, and basically ALMA in its compact configuration falls more or less here between the parking lot and over the soccer field, with the ALMA compact array in the parking lot here. But this is the compact configuration. This is a few hundred meters, which gives you an angular resolution at 1 millimeter, which is of the order of only 0.5 arcsecond, okay? And the angular resolution that we needed for that image is a factor of 100 higher than that, even more than 100 higher than that. So you basically have to go to a bit larger scale if you want. And this is ALMA in the extended configuration, the 15-kilometer baselines, overplotted on the region here. So basically, you can connect our hotel almost with Montreux on the shoreline of the Geneva Lake, which is particularly interesting for the ones like me that are of the appropriate age to remember the Montreux rock festivals. Okay, most of you will not have any idea of what I'm talking about. That's fine. Okay, so. You really need to go to very long baselines to get this angular resolution. That's why ALMA is such a major enterprise, okay? Because you have to build something that is really big and works together, which is not trivial. Okay, so once to go back to this point, once you know that this place is an interesting place, then you can check whether there is something interesting at that position. And one obvious thing to check is whether there are planets in this disk. So this is what we tried to do with. You cannot do it in the millimeter because the planets, even the young planets, are too faint to be observed in the millimeter. And even if they have a circumplanetary disk, in most cases this circumplanetary disk is predicted to be too small to be bright enough to be detected in the millimeter continuum. So basically what one can try to do, one can try to go to similar angular resolution, not as good, I stress, but try to go at similar angular resolution in the infrared, where the planets, as we heard yesterday, I believe, if I remember correctly, are warm and emit radiation, okay? And the contrast with the star is not as large as in the optical, and also you beat a bit the extinction. So that's what we try to do with adaptive optics in the L-band. And if you try to do this, this is what you see essentially, okay? You see a lot of emission that is the disk, scattered light in the disk, but you don't see any point sources. Unfortunately, the sensitivity is still not good enough, I think, to make sure that there are no large planets, because the upper limits that we can pose is of the order of 10 to 15 Jupiter masses, which would be a very large planet. And so I think that we cannot still rule out that there is a planet doing this thing. This big ring is at 70 IU, so you should look at this sensitivity curve. This is the predicted intensity contrast, rather, to the star of planets of different masses as a function of time. This is believed to be a very young object, so you should sit in this area below 1 megayear, where there are no tracks. And at 70 AU, our sensitivity is essentially in this range here. Okay, so there are we didn't show a planet, but it's not excluded. So the take-home points for this first part are that the inner disk timescale, which I said this morning, is consistent with the solar system dating. There is little evidence for mass evolution of the objects that have the inner disk, which is the famous plot that I tried to re-explain at the beginning today. The dust distribution of the disk is well described in the broad sense by the classical theory of a smooth surface density distribution. But when you go and look at the details, these disks obviously are not as boring as they were looking at low angular resolution, as you have seen from the DHL tau disk. Okay, and this I think is a good point to stop for a minute before going to the large grains. And the two topics that I would propose you to think about is what are the possible causes of DHL tau rings, and which observation could help us in figuring out what are the causes of these rings. And then I'll move around since I was, okay, so actually, there is an obstacle in the middle, but I'll go around. So you're taking the time? Okay. Yes. Vai.
La lunghezza d'onda erano le immagini.
C'era quell'immagine che mostrava tre punti più luminosi attorno al centro della stella.
Le immagini ho fatto vedere ora erano tutte... Ah no, ma quella di LBT dici? Era 3 micron e 6. Secondo me è luce scatterata, quella è fatta con una tecnica di... credo abbiano usato la rotation per cancellare la PSF della stella centrale. Quindi quelle alternanza di chiaro e scuro secondo me viene dal fatto che c'è emissione diffusa dal disco e quindi ti crea questi blob chiari e scuri. Yes. There are several ideas. Okay. Yeah. We can. Yeah, let's do it.
But the second question, just a question. What is the magnitude
Of the star itself?
Yeah.
Of the star itself in L band is 8.
and invisible?
This one is not visible. It might be visible also in the group. It's another question.
We will discuss. I was thinking of. Wow. Okay. By actually imaging, they didn't find planets, but would radiant velocities, for example, would give you one if there are.
Yeah, it depends on the planets.
Yeah, that's yes.
Because the question is how massive a planet do you need to do that? And that's the tricky part for that thing. Yes. Yeah, they are in well, they may be resonances. That's maybe.
Like somebody else said that because the disk is so young, you should still have some viscosity, so the resonance shouldn't be.
I should not. Yes, exactly. Exactly. It's so young that because you still have this one is a class 1 source, in fact. So there is still a lot of accretion from the envelope. So that's yeah. Never. Okay, before going to the next topic, perhaps we can briefly discuss this, these two things, since another feedback that I got is that you would like to know what I think of the questions that I posed to you. Well, we don't know clearly, no, what are the causes, but one possibility, actually, is that well, there are two possibilities that are being discussed. There are a lot of ideas run around. One is that these things are caused by planets, but you don't need very large planets to do such a structure, because what you see essentially in that image at 1 millimeter, roughly speaking, is dust. You are mostly sensitive to dust that has a size comparable to the wavelength at which you are observing, not typically. So you are mostly sensitive to dust that is of the order of millimeter size, okay? And millimeter size grains, like those ones, can be confined very easily if you create small disturbances in the disk, okay? And small disturbances now, I mean, I don't have computations, so I don't know whether this is a viable option, but it is possible that you know, planetesimal-like or objects could create enough enough interaction to basically confine those grains. Okay, that's one possibility. And the other, if this is true, essentially, I think this is not practical to detect these things in any way because they will be too faint at all wavelengths. But what if this is really a confinement of large grains? You might be able to see essentially the disturbances in the much lower disturbances in the gas and in the small grains. Okay, and the other possibility is that has been discussed is that these are the effect of some instabilities in the outer disk that are driving these vortices in the outer disk. But I don't know. Maybe Phil and Willy have more ideas on how to explain this. I think that clearly the next step that one would like to do to figure out what they are is to observe the gas. I have not been talking about the gas so far. Is the topic that I will start tomorrow, the observations of gas, of molecular gas in disks. But clearly observing the kinematics and the distribution and the surface brightness and surface density of the gas is a way to try to understand where those structures are coming from. Okay, that's my view at least. All right, let's go in the next 3 hours on my favorite topic, which is grain growth. And I'll actually have to try to do it today because I want to go to the gas tomorrow. So you have heard already about this from the theoretical point of view. In the core accretion scenario, you have to grow the dust from the small sizes up to pebbles that then can form planetesimals. To do that, you do it through collisions, and the collisions allow to grow. So basically, as observers, we can probe 2 regions of this process of assembling planets. We can probe the initial phase, which is what I will discuss today, so the growth of dust to pebble size in the disk, and then we can look at the end state, the exoplanets, as I discussed the first day. And so basically we provide these 2 conditions at both sides for the models to join and explain planet formation. But obviously, it's very hard to trace the other steps. So essentially, observing objects that are between 1 meter and several kilometers is not going to be possible very easily. Okay, so inside the disk there are a lot of processes that going on when grain collide. We have seen this. I thought that I could show these movies of these experiments on the dust collisions that have been described by Willy. You see here some of the things that may happen in the disk. 2 grains that get together and then stick and form a larger grain because they collide slow enough. 2 grains that collide, bounce, and don't do anything, wasted time. 2 grains that collide and instead of creating a larger grain, create a lot of smaller grains, so they fragment. And a grain that collides on a much bigger grain and deposits part of its mass onto the larger grain, okay? So all these processes have been observed in the laboratory, and the laboratory measurements are used inside the models of grain growth in disks to basically describe this process in the disk and describe the global evolution of the dust in the disk. Our goal from my side is to see whether the prediction of those models are consistent with the observations of disks, obviously. That's my interest. And so what are the prediction of a model of grain growth in disks? On top, you have models, and at the bottom, you have sort of predictions, okay? So this first movie here is actually a movie that shows the growth of solids in a disk. I will rerun the movie, but first I want to explain what is plotted. So as a function of radius, okay, in the disk, you have the size distribution of particles in colors. and you see that particles, the brighter the color, the more particles of that size are present, okay? And as you see, the simulation starts all with small particles at all radii. Then you let the disk evolve, well, the dust evolve. The disk is kept fixed, and you basically see that the inner disk is faster in growing grains up to centimeter size, and in the outer disk, essentially, you don't grow. And this is a process that is very fast, taken like this. There is 5,000 years there. Obviously, this is a simple simulation from several years ago. It doesn't include, in this particular case, the radial drift. It doesn't include many other things, but explains more or less what you see. So what you expect to see in these disks are large particles in the inner part of the disk and small particles in the outer part of the disk, okay? That's the basic thing that you expect. This is as a function of radius on the midplane, okay? If you look on the disk in another way, so you plot the radius of the disk and the scale and the altitude above the midplane, okay? And you look and you ask yourself, where are grains of different sizes, okay? You see that the grains settle in the process, so which is included here. The settling is included in these models, okay? So small grains are remain in all the disk up to the high atmosphere because they are well mixed with the gas, and the turbulence of the gas steers them effectively, and as was described today. And then as you go down into the disk, there is essentially an equilibrium between the steering of the turbulence, which is less effectively coupled of grains of larger and larger size, and the force that brings them toward the midplane, the settling that brings them toward the midplane. So basically you have large grains on the midplane, and then you have a vertical stratification. This vertical stratification produces a number of effects that you can observe mainly in the far infrared, because it changes essentially the thermal properties of the atmosphere of the disk, and in the infrared and part of the spectrum when you look at the features and how the extinction goes. And the other thing that you predict with this model is that the scale height that you would measure if you resolve the disk not radially but vertically, the scale height that you measure should be different depending on the wavelength at which you observe, because different wavelengths are sensitive to different grains. Okay, so I will not discuss too much here because there is not too much of this here because there is not much time. The atmosphere and the grain growth in the atmosphere. The only thing that I will focus on the growth on the midplane and what you can probe of the grain population on the midplane, because this is more directly related to where planet formation we think it should happen. And so I go back to this that I discussed yesterday. This is the dust opacity power law index as at millimeter wavelengths. So in this particular case, between 1 and 10 millimeter, roughly speaking, as a function of the maximum grain size, okay? So if we run again this video, okay? If we run again this video, you see that the inner part where there are large grains, okay, should have a low beta index, and the outer part where there are small grains should have a high beta index, okay? That's the basic idea. Okay, but before going to this detailed radial distribution of dust, I want to spend a few minutes on how, on the things that you have to be careful when you do these measurements, and on the results from the integrated emission from the disk, so the average values of the disk, okay? So, this thing is actually an old thing, but is important to keep this in mind, that when we try to measure the beta index at millimeter wavelengths, as I said yesterday, essentially we assume that the disk is optically thin at millimeter wavelengths, and if it is optically thin, then the spectral energy distribution is directly related to this beta index, okay? So if you plot the spectral index at millimeter wavelengths as a function the flux, for example, of your disk. In theory, you should have the flux proportional to the mass and the spectral index inversely proportional to the level of grain growth, okay? So small grains of the interstellar medium should have beta approximately 1.72, so a spectral index that is relatively large. And grains that have grown have a low value of beta, so they should have a low value of the millimeter spectral index. So what happens is that the models that I show here are four sets of families of disk models with different dust properties. Okay, these have interstellar medium dust. These two have dust that is partially grown, and this one is with very big grains. Okay, very large particles. The thing that you notice is that even those that have a low small grains, they start here, but as you move along this line by adding mass to the disk, as I was saying, okay? So if you increase the mass of the disk, at some point you have this turnover in the spectral index. Why is that? Because basically adding mass to the disk, at some point the disk becomes optically thick. And so your basic assumption that the emission was optically thin is not valid anymore. And your spectral index is not related anymore to the grain properties, okay? So they all go there. If you have small grains, obviously this process happens only when you have a lot of mass, because the dust capacity coefficient goes down in terms of an absolute sense, okay? So your measurements in this plot sit in a position like this, for example, and you can explain this measurement either with large grains or with a disk that is without large grains, but a lot of mass that has become optically thick, and that is small, because as I said, I think this morning, when you have optically thick emission, basically your emission is proportional to the temperature times the area. So the larger the disk, the higher you emit, okay? So one important aspect is to make sure that these disks are not small, okay? And they are not optically thick. So that's why I think this was a concern several years ago, but it still remains a concern when you are trying to do this job of resolving the disk emission, as we will see in a moment. You always need to check that this is the right, you are in the right space, that your assumptions are correct, okay? And essentially, with the measurements of the disk sizes that I showed in the previous graphs, all those disks are mostly optically thin, where the emission, where the millimeter emission is coming from. And so indeed, you are measuring the dust properties by looking at this spectral index, okay? The other thing that you have to be careful is that these young stars are not surrounded only by a disk, but typically they also have a wind, for example, and the wind emits radiation as well, and typically emits in the radio continuum at longer wavelengths, at centimeter wavelengths. And so this is an example of what you might expect to see. If you go to centimeter wavelengths, you see the emission from the wind, which is typically a power law. And at millimeter wavelengths, you have the emission from the disk. If you are not careful and you don't subtract the emission from the wind, from the gas, you are basically computing a wrong spectral index here, okay? So these are all technical details that are useful for a didactical purpose. We all take these things into account when you do these things, but it's important to know the limitations, okay? If you then assume that you have solved all these problems, or at least you bear them in mind, then you can, with photometry at different wavelengths, you can plot onto this graph your disks, okay? And this is a compilation from several measurements in several different star-forming regions of the flux, say, at 1 millimeter, scaled for the different distances, because these have different distances, and the spectral index between 1 and 3 millimeters, so roughly speaking at millimeter wavelengths. This was done for isolated mass in the km range, so solar, slightly subsolar. single object. So the binaries were removed from this thing. And what you can see from this graph, roughly speaking, if you, as I said before, in this graph, the mass goes in this direction and the grain size goes in this direction, roughly speaking, okay? So since most of the objects are below this dashed line, which is the interstellar medium dust, you see that the dust in all of these disks is dominated by grains that are relatively large. And if you compute how large they might be, they have to be larger than the observing wavelengths. So here we are comparing 1 to 3 millimeter. This means that the grains in these systems have sizes of the order or more than 3 millimeters, roughly speaking, okay, as average. For the maximum grain size, obviously you have a distribution of grain sizes, but the largest particles have grown to these sizes. Okay, and the models that I showed at the beginning, the model in blue of that show the growth of grains. If you integrate and put, if you simulate the emission and you put it on this diagram, depending on the parameters that you fit in, they fall into this banana shape kind of thing. Okay. So you can explain the massive disk. Now, what's the problem? The problem is the one that was explained earlier today by Phil, and it's the fact that actually, if you are sitting, if you're not just dust particles, but you are sitting in a gas, and you actually need the gas, otherwise you don't have turbulent velocities and you don't have grain growth. If you're sitting in a gas, then the gas is moving typically sub-Keplerian in this disk because it also has a pressure as a function of radius. And so the particles that are decoupled from the gas feel an headwind, they are slowed down and they move very quickly towards the star. And they don't make it to the star because they move so quickly with respect to the other grains that they collide at velocities that are larger than the fragmentation velocity. And so you have the so-called migration fragmentation barrier that is producing the fact that you see here, if you saw the movie is essentially showing that the grains initially grow and then the maximum size goes down again because the large grains are removed toward the star and the fragment. So if you put these models on the plots on the plot that I showed at the beginning, this is the same plot with different colors. So the flux and the spectral index. Here are the measured points, and up here would be the interstellar medium. You see that even if you start, you assume that you start with a disk that has large particles without even worrying of building the large particle, but starting already with the large particle, and you let it evolve, it will quickly diverge from the population, okay? It will go down in mass because the large particles are thrown toward the star, and it goes up in the spectral index because you fragment the large particles and you are left only with small particles, okay? To solve this problem, you have to slow down the drift, okay? If you create models that have some artificial slowdown of the drift, so essentially the way you do it technically in this case, in this particular case, is that you create waves of pressure in the gas distribution, okay? So you create pressure waves, and these pressure waves create essentially a pressure gradient, a negative pressure gradient that confines the grains instead of drifting all in the same direction. If you do this, the drifting is slowed down and your models essentially stay within there. Okay, so it works beautiful, yes, but you don't know how these pressure bumps are made. You just fake them, okay? So the question is, can we detect the traps? There might be very different kind of traps. This is just one example that we looked at just to see whether one could see these traps. This is a gas distribution that is not smooth and uniform, is actually coming from an instability in a very massive disk, so this might not even be the case for these disks. But if you have such a density distribution, then an increase in density obviously creates also a bump in the pressure and confines very effectively the large particles, okay? This is for 50 centimeter grains, but if you look at normal grains, okay, so smaller than 50 centimeters, so essentially grains that are micron-sized grains and centimeter-sized grains. You see here that the micron-sized grains are residing mostly in the outer part of the disk, and in terms of their contribution to the surface density, while the contribution to the surface density of the large grains is mostly concentrated in the inner region and in the arms, you see? Because they are concentrated where the pressure maxima are, okay? And if you take this disk and you try to observe it with the ALMA simulator, you obtain these beautiful images, and you even obtain the, if you look at this, is the intensity map at one, this is the spectral index map at simulated, and this is the, you don't see the details, but this is the simulated observation of the spectral index map, where you basically see that with ALMA you should be able to detect these traps. But to do this, you have to resolve the disk at an angular resolution comparable to the scale height, and with the sensitivity good enough to do the spectral index map, which is about to be available, but it's not yet there. What we can do in the meantime is to use lower resolution data and try to resolve the global distribution of the dust as a function of radius, okay? So check whether is, as expected by the models, you have this progressive stratification of dust grains. And this is the heroic effort that Marco is doing of trying to model at the same time interferometric observations at many different wavelengths, with the goal of essentially separating the problem of resolving the disk structure and understanding the dust opacity profile, and then relate the dust opacity profile to the grain properties, okay? And these are the basic results. This is the beta index, which shows the fact that the beta is relatively small in the inner region of the disk and go to larger values compatible with the interstellar medium grains in the outer disk for most disks. And the grain size, which depends a little bit, as I showed yesterday, on the exact model of dust that you use, but essentially it goes to centimeter size in the inner disk, okay, and millimeter size or even sub-millimeter size in some cases in the outer disk. Okay, now this qualitatively is consistent, as I said, with the models as we saw, with models that have some slowdown of the drift, otherwise it's not consistent, but it's but shows already some diversity that needs to be understood. So there is this funny disk that looks like is large dust everywhere, and there is this disk that looks like having a very steep profile of the dust properties. All of this is still in the early days. There is very few of these resolved profiles available, and I'm sure that with ALMA and the EVLA probably together, it will be possible in the coming years to constrain this part a little bit more and constrain the model as well. Just as a note, because this profile may look very different from this size profile, but actually here we are sampling a region that goes from 20 to 100 AU, roughly speaking, okay? And this region is this region here in this graph, okay? So it's not such a bad approximation, no, to think that this part here in this log-log diagram is a power law, like these things here, okay? We are still not probing the planet-forming region, okay? That has to come. But when you go here, then you have to worry about the optical depth, okay? As I said at the beginning, especially if you go within a few astronomical units. Okay, the other thing that you may ask, obviously, yourself is, these grains grow, is there a time dependence of what you see? The answer is very disappointingly no. So there is no correlation, at least identified so far. I haven't tried some of these statistics for Desperate, maybe I should, but there is no observed correlation between the age of these disks and the beta value. Now, again, The ages are all very uncertain, okay? As we discussed, the individual age of the stars are very uncertain. But the point is that all the objects have more or less the same age, okay? The interesting thing is that there is indication that even younger objects, these are class zeros objects, have large grains. And in fact, Anna has been looking before in her previous life, Anna Miotello has been looking at whether there are large grains already in the envelope that are unfolding in the disk. And there is evidence that the initial phase of growth does not happen after the disk is formed, but is happening as the disk is forming, and possibly even in the inner regions of the envelopes. So overall, I think that speculation can run wild, obviously, but one key thing that we can say is that grain growth has to occur very early, and these grains are present in the disk for a very long time, much longer than one would naively expect. Significant growth happens in the cores and protostars. Possibly there are different phases of this growth, and this is driven essentially by the fact that we see in our own solar system, in the meteorites, that the CIAs are formed at a very specific time, and this could be one phase of grain formation, of large grain formation, and chondrules have instead a continuous formation phase. And so one could, if one would run a speculation, one could say that fast and early you form the CIA-like grains, if you want, and then you replenish the disk over time of chondrules-type grains over the years. Okay, and I finish. I have the take-home points here. Grain growth is observed in disk, so we can observe grain growth, and we can put constraints on the models. The meter-size barrier is probably still a problem. Maybe not to form planetesimals, but at least to retain the dust grains that we see in the disk. And traps are required to sustain the presence of large grains in disk. Tomorrow, I will show some example of traps in different types of disks observed by ALMA. The presence for a long time of sand and pebbles in disks is indeed consistent with the meteoritic evidence of the solar system. Okay, and I'll stop here. Okay, so the question is why we observe HL2 instead of something else, essentially. The reason is that twofold. The first one is that HL2 is one of the brightest of this class. And that's because actually is intermediate between a class 1 and a class 2 phase. It still has an envelope. And so being the brightest, has been studied a lot in the past, so there was a lot of data for comparison, and also we were sure that there was enough signal to noise, even at small scales, that we would detect it. So essentially, this was the reason for choosing it. Yeah. Well, I think that, let's see, if the problem with it is that the contrast is not very, very good in this thing. I can show this again tomorrow, but let's see. Yeah, do we see something here? No, we don't. Okay, we don't see the features that you're saying. I can show tomorrow, but some of those maybe, okay, right, you see it here. So there are some darkest patches here compared to this ring. We don't think that that is a artifact. We think that that is real. Well, those are probably slight artifacts created by the cleaning. Yeah, those are at one of the wavelengths in band 7, if I remember correctly. Yeah.
How often
Sorry, I didn't, it was too close the microphone.
How are pebbles really observed with the meteoritic record of the solar system? As you said at the end.
Oh, so no, what you observe in the meteorites is that they contain these small inclusions, okay, that are coherent, and they have formed together. So we know that at some point in the early ages of the solar system, you had these small chondrules and CIAs that formed, and these are objects which size that go from few millimeters to few centimeters, okay? These are the same sizes, essentially, that we need to explain our observations. So we don't know that what we are observing are exactly identical to CIAs and chondrules, obviously, because we don't see them. But the sizes, the properties that we derive are consistent. That's the point.